we'll go ahead and do that. So anyway, before we get to that, let's just talk about the strength design, criteria, the general philosophy for shear. You already know what the strength design philosophy is for bending moment. Design moment capacity has got to be greater than or equal to the required moment or the factored moment. Same sort of deal with shear, except instead of saying moment, we say shear. So we can say design shear capacity of my beam greater than or equal to the factored shear or the required shear. And if I wrote this in symbol notation, it would look like that. So again, pretty much the same deal as you saw with bending moment. Except now we're talking about shear. Where do you think VU comes from? The diagrams. In fact, you on the first test, you did you took a moment off a moment diagram, right? Well, in order to get that moment diagram, before that, you had to have a shear diagram. Guess what? You already have done this part of it. You might have a beam, you might have loads on that beam. Those loads, if they're service loads, would have to be factored. You'd solve the reactions, you'd do a shear diagram. That shear diagram is showing you V sub U, factored shear, across the whole beam. Now we're going to be interested in certain segments or certain places on the beam where VU is, but generally speaking, you already know how to do this. You've done it. So really, this is what I said, shear is actually sort of simple now because we've already knocked out the VU piece. We just have to concentrate on this, the design shear capacity. This is what my beam does or has to do to resist V sub U. So what kind of capacity is my beam going to have? Well, first off, where do you think the capacity comes from? This is the shear strength of the beam. So the what?
Steel.
The steel, meaning specifically the stirrups, right? So yeah, the stirrups. The stirrups have to contribute to design capacity. Okay? What else do you think contributes to design capacity? Load's all on that side.
Strength of the concrete.
Strength of the concrete. So the concrete. All right? So that's basically it. In this, phi is just going to be a constant. It's going to be 0.75 when we deal with shear. We're going to have two other components that make up the nominal shear capacity, Vn. Those two components, one we're going to call V sub C, shear capacity of the concrete. The other one we're going to call V sub S, shear capacity that the stirrups give us. Okay? So it's really, on the surface at least, it's pretty straightforward. We have a design shear capacity, phi Vn. Phi is just given to you. Vn is made up of two pieces. One piece is called V sub C, shear strength of the concrete. The other one's V sub S, shear strength that the stirrups provide. All right? For the concrete, we're just going to give you one formula. The formula for the concrete is 2 square root of F prime C B times D. They call this the conservative formula for V sub C. There's another formula that you can use that's much longer and much more exact, but for our purposes, we'll always use this one. Okay? Do you know what F prime C is? Concrete's compressive strength. You know what B is? Width of the beam. You know what D is? Effective depth of the beam. You know all these things. In fact, you'll know all these things at the beginning of any problem that you're doing in shear, because even if you were doing a design, these are all going to be things that are known when you do the bending moment design, right? Shear is usually going to be done after that. So you know all these things. The only thing I'd mention with this that throws people off is the square root of F prime C. F prime C here has to be used in PSI. It's an empirical formula. Don't try to think about units. What's the square root of PSI? What's that? What's the square root of a pound? It's empirical. Those are the units don't make sense. It's a lower bound type formula, but use PSI when you're using F prime C here. If you want to change it to kips, this is going to come out in pounds, but if you want to change it to kips afterwards, you can divide by 1,000 and do that. But in this formula, always have PSI here. Okay? So there's another formula you could use, but it's much longer, and quite frankly, almost everybody uses it. It's somewhat of a conservative formula most of the times. V sub S. There's a formula here. AV times Fy times D divided by S.
Is that V subscript?
That V is subscript, right? AV. All right? AV sounds a lot like A sub S. And it is. It's an area of what? Stirrup steel. Okay? Shear steel. AV is the area of the stirrups. Well, here's the deal with AV. Remember how our stirrups typically are U-shaped bars? I mean, and they're probably going to be a small number 3 or number 4 bar. Maybe a number 5 bar sometimes. Probably 3s and 4s. And we've got, if you're looking at a beam, you see a leg that might be intercepting a crack, right? Now, how many legs do you have? Typically 2. There might be times when you have 4. I mean, on bigger beams, they might actually use a double U, a doubled stirrup, but most of the times 2. So if you got 2 legs, what do you think AV is? The area of the bar times 2, right? Because there'd be 2 legs intercepting the crack. If you had a double stirrup, which I don't think you're going to have, but you could have 4, but that's that would be for a bigger beam. Fy, you know what Fy is, right? Yield strength of the stirrup steel. Again, it'll be the same yield strength as your regular steel. D, you know what that is. What's S? Spacing of the stirrups. Okay? So that's what we got going on there.